We're going to do an example of a balance lever, so a place where the fulcrum is preventing this from tipping in either direction. And we're going to analyze the amount of energy involved as an attempt at trying to explain or justify why it is that levers do what they do. So in this example, I'm using a fulcrum that's 30 centimeters high, and I've placed a 3.5 meter rod on that fulcrum, but it's not centered, not necessarily. I'm resting a 15 kilogram block and a 90 kilogram block on there. And the first thing I need to do is to find exactly where to put that fulcrum in order to balance the two. So we're going to start off with our torque equation. So torque this way has to equal torque this way in order for a lever to be balanced. Now torque is the applied force on the left and the distance on the left, equaling the force on the right, distance on the right. Now on the left-hand side, I have a force of gravity, mg, on the left, times the distance on the left, and I have a force of gravity on the right, distance on the right. Now you'll notice that the g's divide out on you, which is handy. So this lever will be balanced on Mars as well as Earth and on the Moon, which is neat, but irrelevant. I'm going to fill in my masses. I've got 15 on this side, and I have 90 on this side. So if I divide both sides by 15, then I end up with distance on the left is 90 divided by 15 is 6, distance on the right. So I don't have an answer for where that fulcrum is, but I have the rod divided into a proportionality. Whatever this is, this has to be 6 times as much. So I'm going to solve that by taking the distance on the left, which is sort of from here that way, and I'm going to add it to the distance on the right. And because there's only one rod, those two distances have to add up to the 3.5 meters. So if I replace the distance on the left with 6 dr, because I just worked out that those are the same, I get 6 dr plus 1 dr is 3.5. 6 of them and 1 of them is 7 of them. And so I would have to divide both sides by 7, and 3.5 divided by 7 is 0.5. So the distance on the right is 0.5. Therefore, the distance on the left then, if it's 6 of these, 6 times 0.5 is 3. And that's handy and convenient and works out and consistent and all those words, because 3.5 is 3.5, which is how much length I had. So I've got myself the place for balancing. So I'm just going to erase this because we don't need this work anymore. And I'm going to think about the amount of energy that I've got involved here. So do you notice that for block number 1, this thing here is resting 30 centimeters above the ground. So it has some gravitational potential energy, mgh. So if I were to work that out, its mass is 15, g is 9.8, height is 30 centimeters, which is 0.3 meters. So if I were to type all that into a calculator, I get 44.1 joules. All right, lovely. Same thing with this one. It's resting 30 centimeters up off the ground, so it's going to have some gravitational potential energy. So its mass is 90, g is 9.8, h is 30. Again, 0.3 because it's 30 centimeters, not meters. And if I pop that all into a calculator, I get 264.6. All right. So in this position, if I have it sitting like so, there's this much energy stored in gravitational potential energy of this particular mass, and there's this much energy stored in that particular mass. So together, the system has these two energies combined. So if I were to take them and add them together, I get a total energy of 308.7. Okay. So when this fulcrum is sitting there, actually I could put that fulcrum anywhere. This thing is, when it's 30 centimeters up, it has that much energy, this much up, it has that much energy. It has this much because it's flat. So what I'm going to do then is to take this drawing and I'm going to tip it so that it's in the other extreme position, right? This mass will be sitting on the ground and this one will be stuck up in the air somewhere. And we're going to look at how much energy is stored in the machine then and compare it to this number. So I'm going to pop this up here so we have a reference, and I'm going to erase the board. So I have this fulcrum here. You see my lever, and then there's the ground, and they conveniently make a triangle. That's not an accident. My fulcrum was sitting here, and it had a height of 30 centimeters, which I wrote as 0.3, just to save us some stress. Now, in my previous calculation, I had shown that the distance on the right, that's from here to here, was 0.5 centimeters, and the distance from here to here was 3, for a total distance of 3.5. All right. Now, if you take our lever, which was flat, and you tip it until the 90 kilogram mass rests on the ground, that has forced the 15 kilogram mass to go up in the air. So my energy calculations have changed, therefore, so I'm just going to try and redo them. This one's easy. The energy for the 90 kilogram block would be 99.8, but it's on the ground, so its height is 0. If you have 0 times something, you get nothing, so there is no gravitational potential energy stored in that 90 kilogram mass anymore. But what about the 15? Well, I'm going to have to use this formula, which means I have to know its height. So I'm going to have to use some triangle tricks for this. Hopefully you can see in this diagram a triangle here. So that triangle looks like it's 0.3 on this edge, and it is 0.5 on this edge. Now, hopefully also in that diagram, you can see a larger triangle. Oops, not that marker. A larger triangle that goes all the way down here, all the way up, and all the way back. And this length, that's the whole rod, that's 3.5 meters. And this side, I don't know. Now, the triangle trick we're going to take advantage of is similar triangles. These two corners are shared, so these sides have to be locked in proportion. So to do that, I just take this side divided by that side, 0.3, divided by 0.5, should give me the same number if I took this and divided it by that. So if you've done some SOHCAHTOA, right, trigonometry or similar triangles, this should be familiar to you. Because these things share an angle, these things are locked in ratio. So if I set them up that way, however I scaled this up to get that, will be the same way I scaled this up to get that. So with my little fraction there, 0.3 divided by 0.5 is 0.6. And if I multiply both sides by 3.5, I get h is 0.6 times 3.5, which is 2.1 meters. So my 15 kilogram block is way up in the air now. Now that I know that height, I can work out its gravitational potential energy. So I'm going to do that. Eg equals mgh. Well, maybe before I do that, just to be clear, this thing was flat, and I tipped it so the 90 kilogram block was on the ground. By doing that, I had to elevate this 15 kilogram block to that height from the ground. So at this new height, it's going to have a different amount of energy. So I just need to calculate that and see how much it is, and then think about this number here and what's happened in this machine. So if I take my mass of the 15, and g is 9.8, h is now 2.1, because I had to lift it higher in the air. 15 times 9.8 is 147, and 147 times 2.1 is 308.7, which is, if you remember, or if you notice, exactly the same amount of energy we had before. So, in the position where the rod is tipped like this, and in the position where the rod is tipped like this, they have exactly the same amount of total energy between the two masses if you add them together, even though they're in different locations. This can only be true if I've placed this fulcrum at the balancing point, so at the spot where this won't rotate. So here's the thing, if it won't rotate here, it won't rotate here either. And it can't do that because it doesn't have any spare energy, right? All of these energies, or all these positions, have the same amount of potential energy in them. And so unless you go in and actually give it energy, either by touching it or adding extra mass, it'll just hang in that position, even though it's not flat. So we're just going to test this little idea here. I did it when it was flat and got 308.7. I did it when it was tipped this way and I got 308.7. If what I'm saying to you is true, I should be able to tip it to the other extreme position where the 15 kilogram is on the ground and the 90 is lifted up in the air, and I should be able to get this same number. So I'm going to clear off the board so we can do that. Okay, so this 15 kilogram mass here, it's resting on the ground. So when I go to do its gravitational potential energy, this happened to us before, this thing would be 0 for this block, so I end up with no energy in that one. For this thing, I have to figure out this height, and you can see in my diagram I have two triangles again, so I'm going to have to build some similar triangles to do this. So I have my smaller one here, like so. So it says that 0.3 divided by 3, well, then let me draw it for you first. Here. It's got a height of 0.3 and a hypotenuse of 3. And then I have the grander triangle here. That has a full length, because that's the full rod, of 3.5. And this height that I need in order to calculate my gravitational potential energy. So I'm using the same trick as before, similar triangles. This divided by this has to match this divided by this because they share a corner in common. So h over 3.5 would be the same as this divided by this is the same as this divided by this. So 0.3 divided by 3 is 0.1. and toss the 3.5 up there. My height is 0.1 times that is 0.35 meters, or 35 centimeters. Okay? So, to do my gravitational potential energy then, mgh, I need the mass of this block, and I need 9.8, and I need the height that this thing has been lifted above the ground, which is 0.35 meters. Now, the theory is, because this thing was sitting at the equilibrium point, it doesn't matter what position I put the lever in, I should have precisely that much energy stored in it, which is why it doesn't move when it's put in that position. So I'm going to have to calculate these things, and hopefully I can get 308.7. So 90 times 9.8 gives me 882. And 882 times 0.35 is 308.7. All right, so confirmed, when the lever is level and the thing was at the equilibrium point, it contained that much energy. When the lever was tipped so that the 90 was on the ground, it had 308.7 joules of energy. When it was tipped the other way, it had exactly the same amount. And if we were to do more complicated math problems, which I think distracts from the point, you would find that any position for this lever as you tipped it, as long as the fulcrum is sitting at the rest point, they all have precisely the same amount of gravitational potential energy in total. So this should combine nicely with all of the other energy topics we've done, where something that's balanced is doing so because it has exactly the right amount of energy to do it. And if you want it to move, then you're going to have to introduce energy or introduce mass or introduce something that will put the thing out of balance. So the practice questions are just two examples of this, one in the extreme position this way, one in the extreme position this way. So you'll have to calculate some heights, get the total energies, and confirm that they are the same in this position as they are in that position.